visualize it, talk about it in a different way, a little less mathematical, a little maybe more examples. Okay, so I will go to see how we can generalize even what the complicated things that Martin talked about, where we have less theory, but it seems to work, to do it not only in one homogeneous case. So the very, very grand goal, ambitious goal, is to understand better nonlinear systems, basically. So we have, in many cases in the world, nonlinear optics and fluid dynamics. In biology, we have nonlinear phenomena, of course, in machine learning today, nonlinear control, and of course in image processing, where we are. So, and you want to see if are there some common basic principles where we can treat. So nonlinear is very, very general and diverse. To not treat every problem single-handedly like just this, but to have some common principles like sparsity, or here we suggest nonlinear eigenfunctions or nonlinear eigenvalue analysis. So the idea is like this. We have the convex area where we understand quite well what's going on. We have the linear case where we understand very well what's going on, which is corresponds to quadratic functionals, which in turn yield linear operators. And we have what Martin was talking about, norms and semi-norms, which in turn yield the zero homogeneous operators. The subgradient is zero homogeneous, and those are one homogeneous functionals, and TV is somewhere there. And in this talk, I would like to extend it a little and talk about nonlinear denoisers, and can we form some spectral thing there. And okay, this is the rest of the world, general nonlinearity, and maybe some of these insights can even be generalized now.
So do you mean one homogeneous or is it two?
No, the one homogeneous functional, it's a zero homogeneous, like the operator, the subgradient is zero. So yeah, this is a little, so this should, because this is quadratic functionals, this is one homogeneous function, so the linear, here it's linear operators, here it's zero homogeneous. So the linear are one, sort of one homogeneous operators, and here it's zero homogeneous operators, like a signum function, for instance. Okay, so I'll talk shortly about the background, the spectral TV. Then I'll talk about the blind spectral frame, how to formulate sort of blindly a spectral framework. And I'll talk more about other applications and problems, future directions of nonlinear eigenvalue problems. Okay, so let's go to the basics of linear versus nonlinear. So, because I'm coming from the engineering world, so this is some slides I show to undergraduate students, so this is some way to connect to them. I have some simple slides like this. So there are the linear sides and the nonlinear systems. And also in learning, of course, you have linear classifiers and nonlinear ones. And in general, linear ones have great theory and numerical schemes, and it's very, very well understood. And the nonlinear are specific to every case. It's less theory, less and well numerical schemes, but the model in the linear case is limited, and of course the nonlinear is the general model. And in some cases we can not only approximate everything by linear theory. So what nonlinear here means, it's like nonlinear operators with where we can work with are things like, this is a very simple one, like this sine function, which is zero homogeneous, and it's basically a derivative, as you all know, of the like absolute value. Okay, and in the linear case, it's like this. And what's here the common thing is this or this are L2 and L1, actually like popular cost functions, and both are convex. So this may give us some sort of a bridge or a way to understand if we have something that works both in the linear and in the one homogeneous case, we can extend it even further. So this is the very, very general thought of to have some common thing here, and then we can go even further to more complex systems. So let's go to, this is repeating a little what the previous talk of Martin did, but I'll do it fast. So this is a decomposition, the linear signal processing system of Fourier. So you have this red thing, this is your signal, and you decompose it into frequencies. So the sum of them gives you this signal, and these are the amplitudes of the sine functions. So what you want, basically from a general decomposition, not only Fourier, you want it, the basic thing is to reconstruct back the original signal, of course. Then usually you want to have multi-scale, like different frequencies, different sizes. Orthogonality is very nice of the different atoms that you have, invariant to certain transformations. And if you want it to be spectral, you associate it with some operator. And for this operator, if it's eigenfunctions of this operator, you would like to get deltas in the transform domain, like sine become delta in Fourier. And usually you want it to also be sparse. This is related to Freddy's talk. And edge preserving in various signals like images, depth maps, optical flow maps, etc. Meaning the atoms themselves, this is usually, if they are themselves can have edges or discontinuities, it is good. Otherwise, like in Fourier, these things are not applicable to. So Fourier has all this basically, but it's not very useful in images, as we know, because it's not sparse for images, and the atoms basically do not handle well discontinuities, so just an edge has all the frequencies in it. Okay, so let's see what's this is a linear decomposition, like a Laplacian pyramid. Okay, so you have the high frequencies here, low frequencies here. As we see, this is only the sharp image we have, and the rest gets blurry. Although if you sum all of them up, you get the initial thing, but it's not a very good decomposition for images. And versus the TV decomposition is very sharp everywhere. It has discontinuous atoms, basically. So then if you start mixing and doing all these games, you can really control, so just the small things, medium, larger, and larger, etc. Okay, so I'm going, so this is the spectral. I won't go very deep into why, etc. But so this is what we found as a spectral decomposition, which Martin talked about and it applies not only to TV but to one homogeneous functionals, and it has many of the desired properties we want. So this is the formal definition, and you can, but generally it applies well. Okay, so we have the reconstruction. It's multi-scale because TV is invariant to certain transformation. Also, this, if you depends on your regularizer, basically, it's edge preserving. As an eigenfunction becomes a delta in this transform, and the question is it orthogonal? Is it sparse? We have some indications that it is, and I'll show them later. Okay, so the basic thing that you can think about is like the fine scales in Fourier are these small signs, and here they're like, these are low frequencies, and here it corresponds to small sort of disks or blobs or something, and larger ones. And it relates to an eigenvalue here by frequencies. Here the eigenvalue of the Laplacian operator. Here it's either the one Laplacian or the subgradient of TV. So the eigenvalue is for disk is 2 over the height and the radius. So larger things are smaller eigenvalues, basically, in both cases. Okay, so I'll give a simple example that I gave the undergraduate. So I'll give him just, they don't know even what TV is, so I'm giving him L1 and see how L1 can be decomposed into its very, very simple eigenfunction. So it's doing a very trivial thing, a little complicated, but the thing is it generalizes to any one homogeneous function. So the associated operator of L1 is this sign function. It can be a set, but it doesn't really matter here. Okay, and the problem, given some signal, U0, decompose it into a sum of eigenfunctions. Okay, and we use, the solution is we use this spectral thing. We do a gradient descent and apply on the solution of the gradient descent a second derivative, multiply by time, and the reasoning is this linear flow here. So the second derivative actually has a response only here. And I'll show a very simple example, just a vector, eigenvectors actually. So this is my signal, and there are three eigenvectors, L1 eigenvectors in this case. So this is with eigenvalue half, eigenvalue third, because it's the height is 3, and the third one is this, and I want to decompose it using this procedure. So I'm doing it everything integer, very, very simple. So what my flow is just, at the next iteration, I take the previous iteration and do a minus of the sign. This is the gradient flow of L1, the integer one, dt is 1 here. And this is what I get for U0. It's the initial signal, and after 1 step, 2 steps, after 5 steps, and this is the finite extinction time that Martin mentioned. And I'm applying this now. So let's see what comes out here. So for the first, what I see that this eigenfunction, for instance, drops linearly. So I'm looking at U1, taking 1 here and here, looking at U2, so this drops linearly, and then when you do this second derivative, you'll get 0. So you multiply this by 2, this cancels out, you get 0 here. But when you go around here and you look here and here, this goes linearly, but this thing disappears, okay? It is here, it is 1 here, it is 0 here, 0 here. This is extinct, and this is this spot here, and then we isolate this specific eigenfunction here. So you can do the computation yourself with a few numbers and see that it works. And then we can isolate by order, it's sorted by order of eigenvalues, the 3 eigenfunctions, and you can isolate them. So what are the eigenfunctions of TV? So there is a theory, so for 2000 already, of this is in 1D, for instance, and in 2D all sorts of these convex blobs, which has some geometric, very specific geometric description, and the value or the eigenvalue is exactly the perimeter divided by the height and the area. So it's really nice geometrically. We understand what eigenfunctions of TV are. This is the isotropic TV in 2D. So, for instance, for a disk, as you see, it's just 2 over the height and the. So as this has more contrast or is larger, the eigenvalue is smaller, meaning it's larger for TV. And then we can apply things like this. So this 4 separated disks become in this. This is the spectrum. So it's just here. It's just the L1 of phi. This is the simple spectrum. So it's just for every t we calculate over x. We just sum the values, and we see these 4 numerical deltas. And if we take all the phi's corresponding, this is going from small to large, so it's a little inverse. So this is like the high frequencies and the low frequencies here. So you want to take out the smallest disk. This is maybe related to what Antonin S. So we have complete contrast preservation in this case, so we don't need any like exotic fidelity term. So here the contrast is preserved completely if we take out the spectral components up till here and remove them and keep all the green ones here. So we get from this, we get 3 disks with complete contrast preservation. If we subtract this from this, we get almost 0 here and just the full small disk here. If we do just TV flow, we indeed get what we know as this contrast reduction. So everything shrinks at different speeds. This shrinks slowly, this shrinks fast. If we want to remove this, we want to wait until this is completely removed, but all the rest reduces their contrast. If we do the subtraction of this and this, we get a lot of residuals of the large ones also. So we can get a very nice spectral of eigenfunctions separation. And this is what happens in real images. Okay, so this is the, we can have a spectrum plot of this strawberry. These are the low pass, but it's edge preserving, so it's not like Fourier. And we can isolate some sort of frequencies, remove them here, have the high frequencies which correspond to here. So we have these gains that were shown before, and we can do it also in a adaptive way spatially, extract some textures, remove some of the attenuated textures or amplify them, and we do it because it's edge preserving and the eigenfunctions are selected to fit exactly the data here, so it comes like quite natural without too many artifacts on the image. And this is what was shown before. So we have these frequencies we can actually manipulate, and because each frequency is an image, we can play with it also. And we have these things, and I have also the loser candidate here. This is before we knew who will win. Okay, and this I showed to undergraduate students, so I showed that image processing, so we have some results, can involve a lot of math and not only nice images. So this is what was talked before. And so a paper on image processing can in some cases look quite mathematical, but not always. So this was a hard work, about a year. And now I'll talk about still nice, but there are still limitations here. So it's very hard from here to go in either direction, because this specific formula applies to the one homogeneous functionals, and it doesn't generalize nicely to Fourier with the specific formula here. So if we do like diffusion flow, apply this, we can apply this. We can take the diffusion, linear diffusion, do this, but we don't get Fourier. Okay, and it's very hard to see how from this if we have non-convex functionals, we don't know what to do then. So we have here, it's very nice. Fourier is known, but we cannot go very naturally from here to here. We cannot go naturally from here to here. So this is what I will talk now. This is part 2 of the talk. Okay, we want to find a common framework here. It's less math, but at least nice. I think we have a nice formulation how to do it and insight. So this is the work I've done with my student Oren Katzir, and Tomer Michaeli helps us on. We need sparsity things, and he's student of Yonina Eldar. He's a faculty in our department in electrical engineering, the Technion. So he helped us. And so what are the insights, how we can connect TV flow with linear diffusion? So we look again at eigenfunctions, and we try to see what's happening here, the behavior of the pixel. So this small disk is under the TV flow shrink fast. This is the red one. We take like a pixel here, see how it goes over time. This is time in the gradient flow. Now linear diffusion. We can take each sign here, it's linear. We can take each sign function separately and analyze how it goes. Because it's linear, we can then add them, and the response will be similar. So the small sine function decreases fast the large sine function, the low frequency one, decreases slower in linear diffusion. The thing is that they have basically the same profile here and the same profile here. Here it's a linear profile, here it's an exponential profile. So the observation here, we look at the decay of each pixel, and they have the same profile but different rates of decay. So if we, to put it more formally, what we can say here is if UTX is the flow in time and space, some scale space flow, so we can express it in these two cases as this integral of a multiplication, a separable multiplication. We have these are the decays here. There are some coefficients, these are those phi's. And with this formulation, we can show that when h is this linear decays, which look like this, the phi's here, we have exactly the spectral formulation. And for linear diffusion, it's an exponential decay, depending on the frequency, and phi related to the frequency itself. So basically, we have now a common thing that this is the TV transform, this is the Fourier transform, now these phi's here. Okay, so we now have maybe a path to generalize things even further. So now it seems like we have some common formulation for Fourier and the one homogeneous spectral decomposition, and we want to go here. So the intermediate conclusions are that the decomposition is based on a decay analysis of the gradient flow. We have a single, like a family of a single decay profile and a whole family which is just scaled by time. So different scales of the same profile decay. And here an eigenfunction decays according to a single decay instance, which will yield eventually this delta in the transform domain. So like in diffusion, a sine function we can is delta in Fourier, and it will have a single flow. So if we want to generalize it to a convex, non-convex thing, so this is our general setting now. So it's now, we don't have a functional, we don't have anything, we just have some nonlinear system that a black box. And so what we do is discrete iterations in time. So we have something, we have our signal, we put it here, we go again and put it again and again and again, and this creates our nonlinear scale space. So we can say this is our initial image, we put the operator once and twice, etc., and this makes us a flow. We want to solve now this part, how to go from one homogeneous to general non-convex. Okay, so here are our assumptions that this nonlinear system is regular enough so the flow can be expressed by a single decay profile like TV. The second thing is sparsity, which relates to the previous talk of Freddy, is that each pixel is composed just of a small set of decays. Okay, so these are our two assumptions, and then what we can do, we can formulate our problem like this. So we formulated something we called a blind spectral decomposition. So we want to say that the flow ut in every place, now this is the continuous formulation, but is approximately an integral of some decays and a coefficient. So this is what we want to minimize now with respect to some decay v and coefficient phi. And this is how it looks like in matrix form. So our flow, we have n pixels here and we have time here, and it's just a multiplication of some different decays and coefficients, and this is a slow decaying small frequencies and large frequencies. So this is the problem, and how can we solve it? Okay, so we're using standard techniques. So we iterate between solutions of minimizing for phi, where phi we assume it's k-sparse. Here we adopt the sparsity formulation, take their IDs, and then we solve for a fixed phi. We solve for the decay profile, which is V, and then iterate between these two solutions. Okay, and unfortunately, couldn't just take OMP or something, matching pursuit, standard matching pursuit, because we have a problem. Our atoms are these decay functions, and they are very, very coherent. It's called in the sparsity community, meaning they are highly correlated. So if those are the atoms, we check the correlation between each atom. So this is 1 here. We see it's basically very, very close to 1. So it's known that OMP and similar strategies do not work on coherent atoms, very, very coherent atoms. So for our case, we knew we have a decay. We have a very, very specific way the atoms look like. So we developed, we call it decay matching pursuit, something for coherent decays. And we show here that this decay matching pursuit, only for this, we have to, from these options, we have to recover what are the best dictionary atoms that can take this line, and OMP and OOMP, another version, do not do it that well. Okay, so the first thing is to check if our model could recover. Now we have a blind model. It's a black box. We do it through sparsity, etc. Do the TV flow. Can it recover spectral TV this way? Okay, so we took this image. Now this is the prototype decay that it found, so it's almost linear. And we compared it. This is TV transform is red, and this is the decay decomposition. This is the blind is blue. You see the spectrum is very similar. And if you look at the images, the blind one recovers spectral TV quite well here, like qualitatively. So then we said, okay, we have something. It seems to work. Now let's go sort of crazy and take very, very highly nonlinear system, but we think it's regular enough. So we hope the assumptions that we had will still work for denoisers. And we took BM3D, which is very known denoiser, very good one. But unfortunately, it's just a mix of procedures that you do, grouping, and then 3D wavelet thresholding, and then you do some Wiener filtering, and so on. So it's a complex system, nonlinear system. No one knows if it has eigenfunctions at all, or what will we do if we do this flow with it and analyze it in a spectral manner. So this is BM3D results. It's known. Besides, of course, all the CNNs, now it was a very good denoiser for quite some time. But the thing is, for us, it's just a black box, very complicated nonlinear system. And from just a small analysis of what it does, we expected that stripes would be eigenfunctions there. And what does it mean, eigenfunctions? It means if you do this flow, iterate BM3D again, 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 so these stripes, all the pixels will decay at the same rate. And the large stripe also will decay. And this is how it looks like. So we took like the pixels here, and they decay like this fast, and the larger stripe decays slower. So we can think of this as sort of eigenfunctions for BM3D in this case. And then, okay, then if we take this image and we remove some sort of band, some spectral band, so we can pinpoint eigenfunctions very well, like in Fourier or in. So what do you think will happen for this image? Okay, so if we can take out these stripes, you see, we just took out some specific band, and we do not change almost anything, and it's sort of in painted there. Okay, you cannot almost see what's happening. And we can do also this. So this is like a known image where you have this illusion of a ball, and these are sort of today's state-of-the-art decompositions. So you have bilateral texture filtering, rolling Gaudius filter, and this is the spectral TV. So as you see, the decomposition here are not perfect. TV does a funny thing. It preserves contrast very well, but it likes balls and round shapes, so it doesn't do squares very well. But VMVW03D likes squares, like it likes stripes, so it can decompose this image into the squares correctly without loss of contrast or anything. And then we can do all these funny things that you showed before, but now for stripes, we can these are the original images. We can enhance some frequencies or reduce some of them, etc. And the images look quite natural. Each instance look quite natural. Okay, so let's now talk about orthogonality. How much time do I have? The clock is okay. Okay. So it's okay. So let's think of orthogonality. So we have, like, for decomposition, if you have just a BM3D thing, what you do to recover like a middle band, you usually filtered a little and then filtered a lot, and then you took the difference between filtering little and filtering much, and this was your band of medium scales. This was the standard thing. So what happens when you do this? We call it subtraction or differences. So if we go to TV, we take the TV flow. If we subtract, these are instances in the TV flow, if we subtract these two images and say it's some sort of way, so what is the orthogonality? What are the difference, okay, the relation here to the original image? So it's very, very high. The correlation is actually 1 in this case, and generally it's very high. For the spectral thing, it will become, the phase will be active only for the small disk in one place and for the large disk in another, and the correlation should be for these two separated eigenfunctions very, very low, so almost perfect. So these are, so both of them are sort of valid decompositions based on the flow. This is difference, this ut is just a difference in time, and these are actually just the second derivative, but it gives a lot of things here for the TV. And so let's see where the components are less correlated. So what we showed, Martin mentioned before, that actually in some this min sub, etc., discrete set like discrete 1D, we can have that the phis are exactly orthogonal if and for different times. The inner product is 0. And this would have, but for isotropic TV in 2D, we don't have a theory. But what if we check the correlation of ut, of sort of the difference at different times? So this is T1 and T2. We check the correlation. So we want that it would be sort of, if it's orthogonal, it would be just on the diagonal. As we see, this is 1 red and blue is 0. So we have very, very high correlation. What happens in spectral TV? The decomposition is almost orthogonal numerically. Okay. When we do the blind algorithm, these are less bands, but it behaves similarly. So the difference is quite correlated, and the spectral decomposition is quite very low correlated, almost orthogonal. And this is how it looks like. This is when you see the images, you understand why it's correlated and not correlated. So this is a difference of this image, like in some instant, some time. So you see this image at band 19 and band 20 are very highly correlated. So if you want to start mixing frequencies, etc., when it's highly correlated, it won't do very good. If it's orthogonal, it's much better. So you see, like this green here appears here, etc. So it's very, very similar images. For the spectral decomposition, as you can see, like this thing does not appear here at all. Okay, it's a little hard to see, but it's almost perfectly orthogonal, these two consecutive bands. Also, what you can see, it's much sparser here than here, and we will quantify it So what happens to BM3D, this spectral decomposition? So this is the difference. So it's less than TV, but it's still here. Correlation, it's not perfect, but it's still much better, I would say. And this is how the components look like. So these are the difference components, which are quite highly correlated, and the spectral components are less. Okay, so we want to quantify how sparsified this decomposition is. So we check in the literature, and there are many ways to quantify sparsity, but this is a very simple one of Hoyer, which does like this. So it just divides any signal, the L1, by the L2. This is the discrete in vector form. So it just interpolates. This is 0 is completely non-sparse. All the vector is exactly the same measurement. And if it's a delta, like so just a single place here and everywhere else it's 0, it's 1. Okay, so you can do the computation and see that it works. And then we can go over the decomposition and examine. So we have a fuzzy way or a soft sparsity measure for things. And we can measure for TV the sparsity of each of the phi and of the ut of the difference. You can see the sparsity of the phi, the spectral sparsity is very, very close to 1. The difference sparsity is much worse. BM3D, we get similar results. Okay, so to recap here, we now have some way to connect Fourier, one homogeneous spectral, and we have some non-convex or more general spectral, a common spectral framework. And we go back many years ago to scale space. Nonlinear scale space helps us define this, and we look at the decay rates. We propose the blind spectral decomposition problem and a way to solve it, and we check orthogonality, and we have numerical indications. The correlation is low of the components. So now I'll talk just a little outside this on what else can be done with the nonlinear eigenvalue problem. So on flows, on graphs, non-convex TV eigenfunctions, and maybe relations even to physics, etc. So this is just a few slides, should be fast. Okay, so there is a flow we propose with my student Raz Nosek, how to isolate a single eigenfunction for one homogeneous functional. So basically the flow does like this. So it has some initial condition, and it goes, and this is a PDE, nonlinear PDE, and it stops when it reaches an eigenfunction. So it's very, very simple and non-parametric way to do it. And you see that when ut here is 0, we have p equals just this. So this is the eigenvalue. Okay, when p is just like up is the subgradient, this means it's an eigenfunction. So these are the only places where it stops. So it stops in many places, but only in eigenfunctions. We also can show that the one homogeneous functional decreases and the L2 norm increases, and this is related to Martin Benning and Burger's Riley quotient, generalized Riley quotient. So it actually minimizes fast because this is going down, this is going up. So it minimizes this Riley quotient, and we know that eigenfunctions, also nonlinear, minimize these things, are critical points of this Riley quotient. And we now work on generalizing this with Jean-François and Nicolas. We have a full discrete analysis and of these types of flows and some results on existence and uniqueness. And this is related also to graphs, etc., where we can, as mentioned before, like have these eigenfunctions of this problem. So this is the first eigenfunction, which gives you this half-moon problem solution. And now we can go further and compute many eigenfunctions, nonlinear eigenfunctions. And this is so this is a little different eigenfunction. It's called the one Laplacian problem, where we have the sign u and not u here. And what we show is that it gives actually bi-valued vectors. Each vector is a bi-valued, and when you can see it as a binary signature sort of. So when you have many eigenvectors, you can actually do some clustering. So it will give you a different signature for each cluster. And this is related, we showed, it's related to something is called spectral hashing, which is proposed by Weiss and al. Here. And it's quite a known paper, apparently. And we have a poster on it outside of Tal here, a student of mine. And another thing is we know that TV, the regular TV, the eigenfunctions are convex. But what happens if we take something like Weikart anisotropic diffusion here and put it here? So it's known to be like Grassmeyer and Lenzen formulas it in 2010. But what are the eigenfunctions there? So here we take this, we rotate in each coordinate according to the level sets. And when it's along the level set, it's standard, it's 1. But here, perpendicular to the level set, we give it a smaller number, basically, so it has less TV there. So what happens is we analyze very, very deeply. This is quite hard work of Shai Beaton. We are in the middle there, but it appears that we can have non-convex eigenfunctions for TV, for this flavor of TV, which looks like this. And I'm almost finishing. So numerically, this is TV, this is AATV, this is the input image. If we do a gradient flow for TV, this is time here. We start with 0. So the blues are 0. And this is what happens to this line here, like cross-section here. So after a while, it becomes some blob here. But for the AATV, you see a linear decay, very, very regular decay. If you compute the subgradient of this initial image, this is how it looks like. This is how it looks for TV. And I'll go through here. But if we divide this and this, okay, this is an eigenfunction. So if we divide, we should get lambda everywhere, so a constant thing. This is what happens here. So this is sort of a numerical proof for showing numerically it's very close to an eigenfunction. So it's almost, the cross-section is almost constant. In the TV case, it's far from constant. So it seems that we have richer eigenfunctions also for TV with some flavors. And the last thing is just, can we connect it also to physics? And we have, this is just something that a review on nonlinear eigenvalue problems, not connected at all to image processing. 2 people I saw from Manchester University in math. You could tell us that I don't know, maybe some of you do know. And they are also in parallel to us solving many nonlinear eigenvalue problems, which are somewhat different. But the question is it related? Can we take from them some theory and numerical methods, or maybe we can solve for them some stuff? So it's very interesting to bridge these disciplines. And to conclude, so we proposed an extension to the nonlinear spectral framework. And very short conclusion, there are just several interesting research directions related to analyzing nonlinear eigenvalue problems. Involves theory and practice. And that's all. And I'm in developing and writing this book. And that's it. Thank you.
So there is time for questions.
When we talk about eigenspaces and eigenvalues of linear operator, we talk about invariant spaces. I don't hear you talking about invariance here. Is invariance here somewhere? You know, like you have an operator, you apply to it something to an eigen function, you get the same function out with an enhancement or a decreased gain. You don't adopt this.
No. So actually, so some things that generalize to the nonlinear case.
So why calling this eigenfunction?
So it's eigenfunction. You apply the operator, then you get the same function up to a constant factor.
That's true.
Yeah, this is true. Yeah, this is so you get an image which is an eigenfunction. You apply.
So the definition of an eigen function is exactly like.
Yeah, yeah. You apply the operator, you get the same thing, up to some lambda. This is the eigenvalue.
Okay, but for example, when you talk about the last thing about about decay and things like this, you were not searching for that.
No. So this is okay.
You did something
Different.
It's a very beautiful idea, but it's not.
Yeah. So why is it? So it is connected to. So we want to say some of the concepts do not generalize from linear to nonlinear. So if you have a mix of eigenfunctions in the nonlinear case, you don't necessarily get that all of them. Yeah, the invariance. But what we saw that is consistent is this decay, even not on eigenfunctions. So this decay profile, you can recover completely the scale. So a gradient flow sort of naturally is constructed from the eigenfunctions of the signal, even in a nonlinear case. So it reveals the eigenfunction, the gradient.
And the recovery at the zero level should be a sum of a weighted sum of these functions.
Yeah, but you have sort of in the TV, but you have an infinite sort of number of eigenfunctions in the continuous case. For TV, like if you can see that every translation, like in R2, maybe it's very easy to see. So even if this sort of an egg is an eigenfunction of TV, if it's convex and smooth enough, so any rotation is an eigenfunction, any translation is an eigenfunction. So surely they are very highly correlated, can be, and they are in principle infinitely many, unlike the linear case. So their eigenfunctions in general are not of TV, are not orthogonal to each other, and are much more than, it's not a basis. It's more like a frame or something like that. But this gradient flow sort of picks the right eigenfunctions for this specific data.
So now if you realize that this decay of pixels is important, why not define this as a general way of processing images?
Yeah. Yeah. Some of the things here will just.
The game is afoot, then you can just do it.
Yeah. Yeah. So.
And then you
the thing is that eigenfunction is a single decay. This is what comes up here.
You can design your decay.
Yeah. Yeah.
Okay.
Okay.
Any other question? I think we can thank you again.